Welcome scholars! Today we will present our paper of VICTR, Visual Information Captured Text Representation, for text-to-image multimodal tasks, especially for the text-to-image generation. We're all from the University of Sydney Natural Language Processing Group. For more details, the code can be found as follows. First, let me talk about the text-to-image generation, which uses only text description to generate photorealistic images. For example, the following text description input, 2 men are riding their horses, is given. The model should produce the relevant photorealistic image. Based on our literature view, all previous state-of-art SOTA model tend to ignore the importance of the text input, but more to focus on the image generation side, like how to generate image in more realistic way. As you can see follows, those computer vision researchers focus on solving the task in their way. All those SOTA models simply use RNN-based text representation for understanding the input text description. However, does RNN-based text representation really include this crucial information for image generation? What do you think? Well, then we thought the task name is text-to-image generation. Then what is the best way to effectively use this input text in order to extract the necessary information to generate the appropriate image? Like what to draw, the aspect of objects, where to draw, the position of objects, how to draw the relationship between different objects. Can we extract those information from the input text description? In summary, our research question is, what would be the best approach to clearly extract the visual and linguistic information from the text description in order to generate the image? So, we will focus on extracting the visual and linguistic information from the input text only, what to draw, where to draw, and how to draw. So from now on, we will discuss how do we extract and integrate this information from the text input. Okay, this is the overview of our visual semantic representation model that we propose for text-to-image generation task. For your better understanding, we will go through the step-by-step process of our proposed model. First, assume that we were given the textual image caption description as input. A man on a skateboard with a brown dog. Then we need to pass the text input to the rich visual semantic information. So we decided to use the concept scene graph, which explicitly represent object instance, their attribute, and the relation between objects. This simple graph representation describes scenes or images in great detail with rich visual semantics using only the given text description. Now let me introduce our text-to-scene graph parser. We firstly recognize the syntactic structure of the text description by applying a universal dependency parser, the Stanford dependency parser proposed by Chen and Manning. However, the output of the dependency parser would not be enough to directly represent the number of objects as well as its attribute and relations between objects. So, we have a semantic enhancement processing component, quantity checker, which aims to detect the number of objects. Remember the first slide? There was a caption, 2 men are riding their brown horses on the beach, right? In that case, we expected to have 2 man objects and 2 brown horses in the image. So we duplicate the individual node in the dependency parsing graph according to the value. We also cover some quantifier expressions like both of, or dozen of, or lot of. In addition to this, we also apply pronoun resolution using coreference resolution and the tensor resolution. Finally, we extract all nouns to classify into object classes and retrieve all adjectives as attribute types of the specific object, which is like a pairwise classification. The relation between objects is detected by the transformer-based predictors if the word is a predicate or preposition of 2 different objects. So now, each text caption of the image can derive one scene graph with a set of object, relations, and attribute. With this extracted scene graph, we now convert them to the vectorized graph representation to produce useful feature representation of nodes and edges in the object, attributes, and relation networks. Here, we apply GCNs, graph convolution networks, to model the relative distance of nodes and edges in the scene graph and preserve this visual semantic information. We made this basic relational graph, which includes each object, relation, and attribute as node level. The object-to-relation connection and relation-to-object connection are represented as directed edges. Similar to this, the object-attribute connection is represented as edges in between. The weight of edges are calculated based on the ratio of the specific type of edges to the corresponding total number of edges. But this scene graph embedding for the objects, attribute, and relations is not enough to produce visual semantic information for the text-to-image generation. So we need this information, where to draw, which can be a positional embedding. The scene graph embedding mainly focus on the semantic relations between objects. For example, the right from the text description, man rides a skateboard. It provides a lingual semantic of object and relations, but it is not still enough to fully describe the image with geographical information, such as location of objects or the relation position between objects. Like as you can see that, we have man in the objects, and then based on what you have in the relations ride or walk, or the other objects, you will come out with different position and location. So, we propose a position-enhanced relational graph that focuses on visual semantics of relations between objects. Here, we denote object and relations at nodes in the graph and uses 6 relative geometric relations, including left of, right of, above, below, inside, and surrounding, which represent the edges from object to relation and relation to object. To train these nodes and edges, the geometric relation is detected based on the gap between bounding boxes of one to another object. And we pass this to the two-layer GCN. Please note that one object may correspond to multiple geometric relations, so we generate individual graphs for each type of geometric relations. Now, the object level and relational level node embedding in each of 6 position-enhanced relational graphs are concatenated and produces the positional object level and relational level node embedding. We now integrate object relation attribute level embedding from basic relational graph and position-enhanced graphs in order to produce the comprehensive visual semantic embedding. The visual semantic embedding is composed to 3 aspects: object level, relational level, and attribute level. Then for each object in one scene graph, the object embedding is finally concatenated with the attribute embedding, as well as corresponding relational embedding, to produce the final visual semantic embedding. So we can say that this final embedding will represent the semantic and geometric information of the object, relation, and attribute in one image. In order to successfully grain this visual semantic information into the text description, we integrate this into the word and sentence representation from raw text. We apply the attention mechanism between the words and visual semantic embedding. The attended visual semantic embedding represents the importance of each object-based visual semantic information to each word in a sequence of the text caption. This attended representation is then concatenated with the word embedding to get the final VICTR representation, visual contextual word representation. Final VICTR sentence representation is almost same, but it concatenated with the sentence embedding. Both final VICTR sentence and word representation are used to generating the image. The three text-to-image generation SOTA model, StatGAN, AttentionGAN, and DMGAN, were selected as baselines. We replaced this original text representation with our proposed VICTR and compare with them based on the generated images. So we evaluated our model performance on COCO 2014, which is the most common benchmark and contains the most complicated photorealistic images with diverse object and relations. In this dataset, each image has 5 corresponding textual description, and we selected the caption, which generates the richest scene graph. We also used bounding box feature to train the geometric relations of multiple objects. For the evaluation metrics, we used IS, FID, our precision, and human evaluation. IS and FID are commonly used for measuring the quality of basic image generation, while that our precision especially measures the consistency between the generated image and the input text. In addition to this, we also conduct human evaluation to measure the human perceived semantic consistency between generated image and the given text caption. So now, firstly, let's have a look at the evaluation result in session score, FID, and R precision. As you can see the table here, the performance of IS, FID, and R precision of the SOTA models and the corresponding improvement with VICTR. Applying the VICTR sentence feature in StatGAN improved overall IS by around 2, which indicates the higher quality of final generated image. Specifically, the original StatGAN achieved 8.45 on IS with 600 epoch on stage 2, while the model with VICTR outperformed the original model at only 130 epoch. For AttentionGAN and DMGAN, we applied the VICTR sentence feature in the initial image generation and VICTR word feature for the iterative refinement. There is a clear improvement for all three metrics for both model with VICTR. The improvement in FID shows that using the visual semantic relation between objects actually helped to form the group of objects in the geographically similar position to those in the ground truth image. Moreover, VICTR was extracted from the original text and aligned with the lingual semantics and visual semantics in the image captions. It helps the model to generate images which are better aligned with the textual captions and leads the increase of our precision. Okay, now let's move on to the final generated image comparison. Firstly, with VICTR, image shows a clear structure, appearance-wise or position-wise, and are also closer to the ground truth than those generated by the original SOTA models. Please have a look at the column 4 in this figure. As you can see, compared to the image generated by original StatGAN on the top row, the image generated by StatGAN with VICTR in second row has more similar structure of ground truth image, that each object, beach, ocean, and sky are positioned from the bottom to top, as well as a kite is flying in the sky and a man standing on the beach. Secondly, compared to the image from the original models, the VICTR-based image provides much clearer object shape, so objects are relatively easier to be recognized. For example, the food and plate in the first column. Also, the VICTR supports the model to well represent contents in the text caption. For example, VICTR is good at handling quantifier into individual object. In column 5 in the image, look at the focus shifts are well captured by VICTR, where the original model fails to identify the number of objects. Another interesting example, as you can see in column 8, even when the ground truth image does not match with the caption said there is a boat, but the ground truth image shows multiple boats. The VICTR-based model can generate the image that are consistent with the caption, so there is only one boat there. Now let's move on to the human evaluation result. We conducted a human evaluation with 50 participants of different background, NLP, non-NLP, undergraduate, and postgraduate. to evaluate our model consistency between generated images and captions. The result shows that all the three SOTA model with our proposed VICTR got a significant higher overall vote rate than the corresponding original baseline models. So you can see the green color bars, right? For more evaluation is available in the paper, different stage evaluation or refinement attention inspection, you can find it in the paper. In conclusion, we proposed a visual semantic representation model which clearly extracted the visual and linguistic information from the only text description in order to generate the image. So further caption mining and representation, embedding model based on the modified object-focused scene graph with the positional alignment into the image, and VICTR enhanced the initial image generation and attentional image refinement by integrating the VICTR embedding into both initial image generation and image refinement process. So this is our reference. So this is our research work. For more details, please have a look at the paper. Thanks for watching, and if you have any question, please ask or send an email to our corresponding author. Thank you.